Once construction and testing are complete, the ship joins a carrier strike group with escort ships and submarines.
From a line on a design drawing, the deck now actually holds about 90 aircraft, numbers that once existed only in the shipyard's plans.
The journey from the first steel cut to the final trial run spans more than a decade, condensed into a single timeline.
Inside the production process, how do they turn piles of raw steel into a floating nuclear airfield of the Gerald R. Ford class? Everything starts from building-sized steel plates, produced specifically to meet nuclear aircraft carrier standards. Each steel plate is cut with millimeter precision, following the 3D model of the Ford's hull. From flat pieces, they raise a massive skeleton, built to endure decades at sea. Instead of building piece by piece, the Ford is assembled from huge modules, each block a section of the floating city.
Easy, easy, watch the wind.
In the dry dock, the bottom of CVN-78 is laid down like the foundation stone of a skyscraper.
From the bottom up, watertight compartments and ballast tanks are arranged strategically to improve stability and survivability.
They first erect the heart of the air wing, the hangar deck, stretching nearly 2/3 of the ship.
The exploded design reveals over 20 decks, each manufactured in a separate workshop before being brought in for assembly. The flight deck, as large as multiple football fields, is built like one huge steel floating runway. Three huge elevators are produced as moving floors, later lifting up to 90 aircraft between hangar and flight deck. In the dock, modules like the hangar are dropped into the growing hull, turning a concrete basin into the shape of a floating airfield.
The island is built at its own module, smaller and set further aft to maximize flight deck area right from the design phase.
In a highly classified area, 2 reactors are built like miniature suns, later powering the entire ship.
Check connection port 4, green light.
3, 2, 1.
Reactors weighing thousands of tons are lowered into the hull with absolute precision. Turbines and reduction gears are installed after the reactors, converting nuclear heat into motion for 4 propeller shafts.
Each propeller is cast and machined specifically for the Ford, towering over a grown person. At the bottom of the dock, 4 propellers are bolted on, ready to push this 100,000-ton floating city at over 30 knots.
Reactor critical. We have power.
Hundreds of kilometers of cables and pipes are laid before bulkheads and interiors close them in, forming the ship's nervous system. Before the flight deck is fully closed, EMALS tracks are sunk beneath it, completely replacing the old steam catapults.
Beneath the steel skin, synchronous linear motors are laid out like bricks of magnetism.
Once hull, hangar, elevators, and EMALS are ready, the flight deck is placed as the final skin of a giant mechanical creature. Elevators are cut through the deck and tested to move smoothly between hangar and flight deck right in the dock.
The compact Ford-class island is welded into its aft-shifted position, freeing up maximum forward deck space for aircraft flow.
Inside, spaces like airboss, radar, and the bridge are finished like the control rooms of both an airport and a warship at once.
Radars and phased arrays are mounted, ready to scan the sky for swarms of targets and future drones. Close-in weapon systems like phalanx are installed and movement checked before being fixed along the ship's edges.
Defensive weapons like Sea-Ram and Sea Sparrow are brought aboard in modules, turning the giant steel hull into a fully armed base.
Magazines are placed deep in the bottom, with thick reinforcement to minimize fire and explosion risk. This floating city needs sleep, so living quarters are finished along the hull, both forward and aft. 2 large mess decks are built like compact university cafeterias, serving around 5,000 people. Right on the ship, a mini-mart is completed, so sailors can shop as if in a city ashore.
The engineering hangar is equipped to remove, service, and reinstall jet engines, the heartbeat of the air wing on deck.
Laundry and gear storage are placed near living spaces, sustaining the daily life of this floating city.
The radar room and CDC are finished as the nervous centers where all future battlefield data will converge.
In the CDC, layout of consoles, screens, and cable runs is calculated to handle massive real-time information loads.
Right below Airboss sits the bridge, where the captain will command this $13 billion airfield at sea once it's complete.
Testing. 1, 2, 3.
Generators linked to turbines are installed in a row. Enough power for a city of 100,000 people.
High-pressure piping links the reactor to steam generators, turbines, then to condensers, forming a closed thermodynamic loop. Before launching real aircraft, the EMALS shuttle runs the track to validate acceleration, electromagnetic braking, and smoothness. The modern AEG arresting system is mounted beneath the deck, with steel cables stretched across, waiting to stop tens of tons jets in their tracks.
Jet blast deflectors are attached, ready to shield equipment and people from the extreme heat behind aircraft. .50 caliber gun positions are marked and mounted, forming the ship's nearest defensive layer. In the command center, control software for phalanx and steps.
After years in the dry dock, water flows back in, and the Ford-class carrier floats free for the first time on its own weight. Guided by tugs, the Ford leaves the build dock, carrying millions of man-hours from tens of thousands of people.
At the pier, dry tests are run, from reactors, turbines, to electrical and control systems.
Turbines spool up. Propellers spin in still water. Every sensor closely monitored.
Once the aircraft is at the launch, return to 120.
EMALS is tested with different loads, from fighters to UAVs, to ensure smooth and safe acceleration. The AAG system uses test sleds instead of real aircraft at first, checking its ability to stop in just a few dozen meters. At a test range, weapon systems fire live rounds at dummy targets before the ship receives its combat certification.
When the technical backbone is stable, every small detail, room signs, handrails, final coat of paint is completed.
After years of construction, USS Gerald R. Ford is officially delivered, but its sea trials are only just beginning.
On open water, the ship is pushed to its limits. Speed, maneuverability, and system response in all conditions.
Harmony between the new electromagnetic launch system and the steel structure born in the yard. Bases like CDC, Radar, and Airbus are woken up, running as in combat but under safe test conditions.
Once construction and testing are complete, the ship joins a carrier strike group with escort ships and submarines.
From a line on a design drawing, the deck now actually holds about 90 aircraft, numbers that once existed only in the shipyard's plans.
The journey from the first steel cut to the final trial run spans more than a decade, condensed into a single timeline.
As one Ford leaves the yard, the frame of the next is already growing in the same dock, the production process starting over again.
Compared to Nimitz, the Ford class was designed from the outset for large module construction, reducing block count, welds, and simplifying assembly.
Dyson. The whole production process is digitally simulated, from design, material flow, block schedules, to sea trials.
From naked steel frames, layers of paint, wiring, pipes, and fittings turn it into living and fighting space for thousands of sailors.
The hangar transforms from an empty steel void into the parking, maintenance, and rearming hub of the entire air wing.
Every time an aircraft leaves the deck, few think about the welds, steel blocks, and cables hidden below. Behind the $13 billion price tag are countless pairs of hands, each weld a timepiece of strategic deterrence.
Building a new class like Ford is a balancing act between technological innovation and risk, with costs ticking up year after year.
Digital analysis runs in parallel with construction, ensuring the hull can withstand tens of thousands of launches and recoveries over its lifetime.
From steel ingots in a furnace to a warship on the waves, the Ford-class production process is a massive assembly sequence.
As the deck lights gradually dim, beneath the steel lies a maze of machinery placed with millimeter precision during years of construction.
The words USS Gerald R. Ford are not just a ship's name, but the outcome of a nation-scale production effort. We create 4K 3D animations to take you inside the production process of the Gerald R. Ford class aircraft carrier.